Yeah, so let us start with a quick introduction. Let us say that we have our design. We have some requirement, and we want to implement our design in some digital logic form. We want it in a hardware form on some FPGA board. So how do we go about it? So let us take an example that we have a full adder design, and we want to actually implement it in our hardware on our FPGA. So what would be the first step? First step, we are expected to use K-map or truth table and different optimization techniques, and we have to find the expression for sum and carry of the full adder. Once we are done with that, we exactly know that okay, we want AND gate, we want OR gate, we want XOR. After doing that, we can write our VHDL code. So that will be mostly our structural kind of VHDL coding. And then once we have our VHDL code, we identify the test cases. Let's say we want to make a full adder. It will have 3 inputs. So can anybody quickly answer in the chat box that how many test cases will be generated for 3-bit input? Okay. So yeah, correct. 8 is correct. So let's say now we know these test cases. We give these test cases into a trace file, or we just add it to the test bench. We will discuss about this later. And once we know these test cases, we go for synthesis. So basically what the Quartus tool does is, we have given the VHDL code, it will convert it to some gate level design. So it will use some basic logic gates like AND or XOR, etc. And it will make a gate level design out of it. After synthesis, we can go for RTL simulation. So what is the meaning of RTL? RTL is basically register transfer level. That is, we are assuming that our design is like our combinational circuit is infinitely fast, and we don't consider the delays in routing our design or the delays due to our gates, and we just consider it logically. That let's say the data is sent from the input and it is received at the output. We are just interested in the values and we don't consider the glitches, the delays, etc. So that is RTL simulation. You can also think of it like some ideal simulation where there is no glitch or there is no timing issues in it. After that, the Quartus tool does fitting. So fitting is basically what we have our gate level design at AND gate, OR gate, XOR, etc. But let's say our CPLD or FPGA device in which we are planning to put our design, that may not have that kind of internal structure. So basically the Quartus will convert our design into some different designs such as lookup tables or whatever the design our device needs. And after this fitting is done, we again go for gate level simulation. In gate level simulation, we actually come to know the real timing errors which may come out or the glitches which might be seen in. And with that, again, we have to, if we see some glitch, then again, we'll have to repeat the process. We'll have to again correct those debug and then again reach here. After that, let's say we want to put our design in an FPGA. So FPGA device will have some inputs, it will have some outputs. So we want to specify that to the device, to our Quartus, that okay, this is the input, these are the input pins, these are the output pins, and that will be decided by how our PCB is designed. And then again we do the complete design compilation, and it also includes fitting. And then we will go for programming the target device. Programming is basically we will download our program or we will burn our design into the device. And then we can go for actual testing. I mean, once we have that design into our device, we will power on, I mean, we will use our board, and using the board, the PCB, we can actually test, we can actually give it some inputs and check the outputs. Or there is automatic technique called scan chain, and we will discuss about scan chain later on. So does anybody have any doubts in this? Like, please raise your hand and then I will give you a chance if anybody has doubts in up to now what we discussed. Okay, so I don't see anybody having doubt. So I will just go ahead. Yeah, so today we are going to look at these aspects. So just to start with, like most of you might have read the Professor MPD's document, this slideshow which he has shared with us. So let us have a look at what is CPLD and what is FPGA. So most of you might have understood what is PAL, PLA. So I have a question for you, that let's say we have some digital circuit or some design in our mind, and it has some inputs. Let's say it has 4 inputs. So can we implement any logic using memory? Let's say we have a RAM of that much size. We have 2 raised to n. Let's say n is the input. We have a RAM of 2 raised to n bits in size. So can we implement our logic in that RAM? This is the question. You can write in your chat box. Whether is it possible if you have only a RAM, you don't have AND gate or gate. I mean, you have a memory basically, or a table, let's say. Think of it like some truth table or something like that. So is it possible to implement every logic? Would you write in your chat box? Yeah, correct. So most of you have got it correct, I think. You can implement any kind of logic if you have a RAM. So a similar concept is shown over here, that LUT is basically like a RAM which can store the output for each input combination. So CPLD consists of blocks which are called configurable logic blocks, and each configurable logic block contains this PLA or LUT. In nowadays LUTs are used. Earlier CPLDs used to have PLA kind of design. So these lookup tables are inside the CLB, and then the CLBs are connected with some interconnect in the device, and then these are connected to the IO pads or the IO outputs of the device, or the IO blocks we would say. Similarly, FPGA has a large number of such CLBs, and they also have an interconnect matrix. So let's say we have a large number of CLBs, and then there is an interconnect matrix or interconnect switch, which can switch between different connections, and it can make different connections. So I have a question for you all, that for a big design, let's say I have a very big design, then is FPGA better or CPLD better in terms of implementation? Can anybody answer? Yeah, correct. Most of you have got it correct, that FPGA is better. But can anybody tell me what are the drawbacks of FPGA? I mean, let's say I have FPGA is always a big design, it has a big implementation. Then what might be the possible drawbacks of having an FPGA? Can anybody answer in the chat? Okay, I don't see any answer. Yeah, costly. Yeah, that's a correct one. Limited block RAMs. Okay, but let's say as compared to CPLD, what might be the limitations? LUT will have to store some not so useful combinations. Okay, but FPGA has a large number of LUTs, so I don't really worry about it. So there are some main disadvantages of FPGA, that FPGA is a volatile kind of design. I mean, once you power on your FPGA, you have to again program it. Once you power off, it will lose all its program or all the design that has been entered into an FPGA. So you have to again and again keep on reprogramming it when you power on your FPGA. So there are many more such disadvantages. FPGA is also very much complex, and in terms of timing, let's say we want some fast and predictable design. In that case, FPGA might not be that accurately predictable. It may be a little slower or a little complex in that terms. Okay, so now once we know about CPLD and FPGA, let us look into Max5 CPLD. I mean the CPLD in our board in Krypton which we are using. So it has a similar structure. It has many logic elements in it, and many such logic elements are added in a logic array block. Intel calls it LAB, and then these are connected with the multi-track interconnects. And each logic element, as you can see in the slide, it will have a lookup table. It will have this carry chaining. So basically, it can be cascaded. I think most of you might have studied about carry select adder. So let's say there is some carry coming in from the previous block, and we have generated some carry which we want to forward it to the next block. So that is available. And we have a register as well. So register, you can think of like 1-bit memory in that. So it has all such features in a logic element. So it's quite advanced kind of CPLD. So we will go ahead. So let us start with Quartus. We will create our project in Quartus.
Just a reminder, you do not have to do in parallel in your PC. For now, just look what is shown to you, and after that only you will do.
Yeah. So just I want to confirm once, like, are you able to see my desktop? I mean, not the presentation.
No, I don't think so.
Okay, one second, I'll just restart sharing. Yeah, so now is it visible? Can somebody speak out?
No. Yes, it's fine now.
Hello. Yeah, okay. So I have opened Quartus, and can everybody see the Quartus window?
Yeah.
Okay, fine.
You are muted.
Yeah, so in this, I want to enter the directory where I want to store my project. So I will just enter that directory.
Daya, please start from the beginning.
Okay, fine. Okay, so as soon as I open Quartus, it will look like this. This will be my home screen, which you can see in the center. And I will see new project wizard option over here. So since I want to make a new project in my Quartus, I will select new project wizard. Then I can see a dialog box which has introduction kind of, it is written in the title. So I will just go next. So here it will ask, where do you want to store your project? So I will select that directory where I want to store my project. Okay, so I will just create a new folder over here. I will give it a name as demo. And select that folder. Now it asks what is the name of your project. So I will give the name as demo experiment or just demo. Then it will ask what is the top level design entity. So here you should understand that top level entity is the main design. I mean the input and output of your top level entity will be actual input and output of your main design that you want to implement in your FPGA. So let's call it as DUT. I will show what is this DUT later on. Then go to next. So here it will ask whether you want empty project or template. So I will select empty project. We need empty project. And go to next. Here we can add files in our project, but I will show how to add file later on. Right now I am not adding any files. Yeah, so this is the important part. So here we have to select which device actually we want to program, or in which device we actually want to implement our design. So we want to use Max5 since our Krypton board has this Max5 CPLD. I'm selecting the family as Max5 or Max-V it is written, and I can search my device over here in the name filter. I will select 144. Yeah, so below over here I can see a list of devices. So I will select the appropriate device. Our device is 5M1270ZT144C5. So I have selected my device. It shows how many logic elements it has. And I will go to next. So here in simulation, you have to select Model Sim Altera for simulation. And in the format, you will have to select VHDL over here. This run gate level simulation is not necessary right now, so I'm not checking that one. And I will go for next. So here you can see the summary. In the summary, you should once confirm that your device number or the device name is correct. And then you can finish it. Okay, so this new project has been opened. Now I want to create a new file for programming. So in the left side, there is a direct quick shortcut for creating new, or I can go for file and then new. Then I get this various files. So I will select VHDL file since I want to write a VHDL code in it. I will say OK.
Gaurav,
Yeah.
there is a slight lag between your audio and video. So means better you hold a while means in a particular window.
Okay, fine. So shall I repeat from a new file or is it okay? Was it visible?
You can continue.
Okay, fine. So now you can see that I can write over here. I can write my code over here, but since we already have those files, I will be showing for full adder case. And in the Moodle, in the Teams, we have this full adder code files over here. So this folder I have already downloaded over here. And I will be using these files for the demo. So I will open that folder first. So in this folder, I have a full adder code already written with me. So I will just add that full adder code in my main code. I will save this file, give the entity name as the file name. So I will, while saving, I click Ctrl S. So here I will give the name full adder. And just ensure that the type is .vhd or vhdl over here. Then click on save and it is saved. So let us once quickly go through this code over here. So this is a entity full adder, and can anybody quickly tell me that how many input output ports are there to this entity? Correct. So it has three inputs and two outputs because entity shows what are the inputs and what are the outputs and what is the type of input and what is the type of output. So I will go ahead. In the architecture, we actually specify what is the structure of our full adder. So in this,
Gaurav, will you please explain the lines? Just 2 lines only.
yeah,
Roadmap.
yeah, sure. So port is basically, I mean, in the entity in basically tells you that these are the input ports A, B, and C in. And this out keyword over here will tell you that S and C out are the output ports. Now, what is this STD logic? Can anybody tell me what is the difference between bit and STD logic? I will check the chat box once. What is the difference between, yeah, correct. So STD logic has actually 9 values possible. So whenever you will be simulating your design in actual hardware, you may get some values which are, let's say you want to have high impedance or you want to have don't care or all different kinds of values. You can have that in STD logic. And bit can have only 1 and 0. So I have specified STD logic. And now I want to specify the architecture of my entity. So architecture will basically tell me what is the internal structure or what is the internal working of my entity. So I have declared these as signals. So signals are basically like wires. I want to have some wire connecting from one component to other component. And so I have declared these signals and their type is also STD logic. Now in the architecture, I have this half adder and I also have these OR2 and 2 XOR. So again, I have a doubt in this that where are these defined? I mean, where is the architecture of this half adder on and or defined actually? Because in my code, I don't have any such definition. So can anybody answer me? Yeah, correct. You are correct that whenever you want to add your own package, whenever user wants to add his own package, you can do it in work.package. So my package name is git and it is in the work library. So I will have to add these files now, right? I have connected these devices over here. I have connected this and half adder and or everything according to my design. And now I want to basically add this library in this. So I already have all those files, so I will directly add those files. I will show how to add the files in the project. Before that, let me just copy them. Yeah. I have all these files copied in my project folder. I will add all of them. So either you can go to project, add remove files, and here click on this button, triple dot. So once you click on this 3 dots, it will ask you which files you want to add. So I will add this DUT file. So I will explain what this DUT means. And here you can see that I have one file called gates. So this is my library, which is actually having the architecture of all those gates that I have declared. So I will also add those. I have selected these 2 files and I'm clicking open. Yes, so I can see these added over here. I will click on apply and then OK. So in the project navigator over here in Quartus, if you select the files option, you can see the files added in your design. So in this, don't forget to do one thing, that right click on dut.vhdl and set it as top level entity. Okay, so here you can see that I have opened gates.vhdl and I have all my architecture definitions over here. So I can safely have these components in my design. Now let us see what DUT means. So I will switch over to the PPT. Yeah. So is this visible to you? Is the PPT visible?
Some 10-second lag, but yes.
Okay, fine. Okay, so this PPT, actually this design is our full adder in this PPT, if you can see. And this DUT is just a entity which actually defines these as input, inputs as many as our design has and outputs as many as our design have. So I will once show you. So this is our DUT file. In this we have to declare the component full adder. So this should be exactly same as our full adder entity. One second, I'll just show you. So this full adder entity should be exactly same as our component. It should have the same number of inputs, outputs, and everything should be same. So I have added that component and I just want to instantiate this component. So I will tell my DUT, or I will tell my compiler that I want to add this component inside the DUT as it was shown in the slideshow. And this DUT has inputs called input vector and output vector. So I want to just connect this input vector bit by bit. So once I will tell you what is this input vector is, basically a collection of STD logic. Each bit is STD logic in the input vector. So this is 2 down to 0. It means it is a 3-bit long vector. Or you can think of it as a collection of different pins or collection of different bits. I have one question. What is the difference between vector and a bunch of pins, or an array of, let's say, pins, or array of bits? What is the difference between vector and array? Oh, hello. Yeah, can anybody just tell me that what is a vector? Array is bit accessible. Okay. Yeah, correct. Okay, so this answer is correct, that in an array MSB and LSB is not defined actually, but in a vector MSB and LSB are important. I mean, they have sense in vector. So we have this vector, STD logic vector, and we are connecting our inputs. I mean, the inputs of this full adder carry in A and B to the input vector, and we are connecting the outputs of our full adder to the output vector. So does anybody have any doubt in up to here? Yeah, both are bit accessible, I mean arrays and vectors, but this is the main difference. So does anybody have, I mean, they can raise their hand and speak out if they want. Do you have any doubt up to here? Okay, fine, I will go ahead. So this is our DUT. Now we will just compile our design. I clicked on this icon over here. So once it is done, you can see here that analysis was successful, 0 errors. So there was no syntax error in my design. I will open an RTL viewer to just show you what has been generated or what the programming tool has interpreted. So this is our RTL view. And this is, so basically right now it's just showing one block, that full adder. But if I look into it, I can see all the blocks that I have connected, that is half adder, AND gate, OR gate. And I can also see what is inside the half adder. So here I can see AND and XOR gate. So it is as expected. You don't have to do this step every time. This is just to show you that yes, it has interpreted our design correctly. So I will close this window. Okay, so now basically we want to simulate. See, is it possible if we just keep on checking in the RTL of the design in such a manner? Is it possible to verify large design? Let's say we have some big processor, we want to make some big processor or something, and if we just make this kind of RTL and we just go on checking this RTL, it's not possible to actually check our design. So for that we use these test benches. So in a test bench, we actually give the inputs and we check the outputs of our design. We simulate it and we check the outputs, and then we compare with the actual expected outputs and the actual outputs. So now we are going to do that. This is our test bench. I mean, if you can see this slideshow. So this is the structure that we would be using. So this is our DUT, and we will connect our DUT to a test bench code, which will be a VHDL code again. And it will take the inputs from a trace file. The trace file will also have the expected output as well. So it will take both of them. It will apply it to the DUT as the input, and the outputs it will compare again with the expected output that it has got from the trace file, and then it will give the actual outputs, or if there is an error, it will write as error in the output file. So this is how a test bench works, and it will also give a message whether it is successful or our design has failed, the test cases have failed. So this is possible. So I will just show you how to add a test bench. So you can go back to again add and remove files in the project, and there in the left in the category section under ADA tool settings, you will see a simulation option. I will click on that. Then in the native link settings, I will click on the radio button, compile test bench. Then I will click on the test benches button, and then a dialog box appears for test bench. In the
Can you
dialog
move a
box,
little slowly? It is lagging.
okay, fine, sorry, I'm sorry. Okay, so in the dialog box, I will click on new. So a new dialog box appears, a new test bench settings dialog box. So in this you have to write the test bench name. So this test bench name is basically the file name of the test bench file that you are going to use. So we will be providing you this file. You just have to make minor modifications in this file according to your design. So now we will just see that file once. So I have opened the folder where I have downloaded all the files from Teams. Now I will open test bench file. So is the test bench file visible to all? I mean, somebody can just speak out.
Yes, it is.
Yes.
Okay, fine, thank you. So this test bench, yeah. So what this test bench has is all the code that it will read those files and it will apply those to the DUT. So you can see at the end there is this instance of a DUT. So in the beginning we have to just change here the number of inputs and number of outputs. So I was implementing a design for full adder, but you may need different number of inputs and different number of outputs. So you have to update it accordingly. Then actually you are not expected to write a complete test bench on your own. You can use this same test bench and just do some minor modifications as you require. Here you can see that it will open this file trace file.txt to read or to take the inputs, and it will write in outputs.txt. These outputs are the actual outputs that are obtained after simulation. So I will just go below. Here you can see a code, wait for 10 nanoseconds. So this statement tells the Quartus or the simulation tool that you have to apply the input, you have to wait for 10 nanoseconds for the outputs to settle, and then you have to go for the next. After that you have to again wait for some time. The next statement is a little bit after that. Again it will wait for some 4 nanoseconds after taking the output, and then it will apply the next output input, and this will continue as long as you have inputs in your file. So here you should remember one thing, that you should just ensure that what is the label of this DUT component that I have used. So I will just copy this name, we will need it afterwards. And I am closing this test bench. Anybody has doubts in this test bench? Would you please raise your hand and speak out? Okay, yeah. Why do we need to wait for the circuit to settle? So let's say we are implementing our design in an FPGA or a CPLD, and there we have different kinds of gates and different logic blocks. So it will take some delay for the output to appear. So in that case, you will have to wait for some time. Maybe you don't have to wait at RTL level. Yeah, sure, I will explain this. So maybe you don't have to wait for RTL level simulation, but whenever you want to simulate at an actual implementation or actual gate level, I mean, you want to simulate your delays, at that time you need to wait for some time according to the delays. Yeah, I will just go to the assert statements. Yeah, so this assert statement, basically here there is a error flag kind of variable. See, if you can see here, I have here this variable which is boolean, true or false, and there is a error flag. So in my complete loop, whenever I encounter some error, that is the difference between the expected output and the actual output, I will directly set this flag to true. So what this assert statement does is, if this condition, I mean the condition in these brackets, if you can see this error flag condition, if this is false, then it will report this string. I mean, it will display this string, success, all test cases are passed. So this string will be displayed in the simulator interface. It may be model sim or whichever simulator you are using. We will use model sim. So in the console of model sim, you will see this message. And if this is true, let's say if this flag is true, I mean, not of that. So if it is true, you will see this failure. So is it clear?
Could you explain it once again? I didn't get it.
Okay, sure. So whenever this condition, I mean after assert, we write a condition in the brackets. So whenever this condition is false, it will display this string which is written after report. And this severity statement, this severity will basically tell you what kind of, I mean in the simulator interface, it will show as note or it should show as an error. What exactly it should show it as. So these are only specific kind of severity. You can either have warning, error, or a note. And this string will be displayed. So is it clear now?
So assert statements give out values only when the argument is negative, like.
Yeah. So it is false. So when let's say I have an error flag, my error flag is set to true. Then my argument becomes true, and then it will not show that success message. Instead, it will go below, and there I have inverted that complete condition. So there it will show failure.
Okay. Thank you.
Yeah. Okay, so this is our test bench. Now we will just go back and check what are these trace files and output files once. So we have, let's say we want to identify what are the test cases for our full adder. So I will go there. But before that, I will just fill this new test bench settings in the Quartus dialog box. I will write the name of my file, test bench name. It is testbench.vhdl. Yeah. Now here it will say top level module in test bench. So this is your entity name in the test bench. The entity name is a test bench again. So here you can see the entity name is test bench. And now the name of this DUT instance. So whatever label it is here, generally it is DUT instance for all. So don't change it unnecessarily. You can copy this directly. And in the Quartus dialog box, if you check this use test bench to perform VHDL timing simulation, it will show a text box for design instance name in test bench. So in this design instance name, this is the label that we copied earlier. So I will paste it over here. Then I have to add my test bench file to my project. So I will click on these three dots. Now a dialog box appears for the browser. So I will have to add two files. One is my testbench.vhdl and another is my tracefile.txt, because as you have seen that trace file is being read by the test bench. So if you don't add that trace file, then you may get some error during simulation. It won't find the trace file. So I have added both these files and I'm clicking on open. Just ensure that you can see both these files over here. Then click OK. Then again in the earlier dialog box, click OK. Okay, so now we have added the test bench, and in the main dialog box, I will just say apply, and I will click OK. So these test bench files are added in my project for simulation. So once I will just compile it. Okay, so I can see success. So now I want to do RTL level simulation. So this RTL doesn't consider the timing delays or some what we can say glitches that may appear. So I will just perform this RTL simulation. And go to tools, then run RTL simulation, and I will click on RTL simulation button. So it will take some time to launch Model Sim Altera. Yeah. So if you can see this transcript, if you can see a note success. So this note is the severity level that we have specified over there. And it's showing that all the test cases have been passed. I have got the design as expected. I have got the output as expected. So this is a zoom button that I am clicking just to see my wave window. So here I can see the waveform of the input and output. So these three are the inputs and the lower two are the outputs. So I can say that my full adder design is working at RTL level. So we'll once again visit that trace file that I had discussed earlier. Yeah. This is the trace file.txt. This trace file contains inputs, all the possible inputs over here, because my adder is 3-bit adder, so it will have 3 bits. I mean the full adder, and it will have 3 bits, and the expected outputs. So one is sum and one is carry. But here just you have to take care that your MSB and LSB are correct. So the leftmost is the MSB and the right one is the LSB. And after the space, this is the output, expected output. So this expected output as leftmost is the MSB and the rightmost is the LSB. In DUT design, we have actually specified that LSB is the carry and MSB is the sum. So accordingly, we are getting the outputs. So if this is 1, 1 and we get carry as 1 and sum as 0. So these are the expected outputs. So this test bench should check whether these outputs, the actual outputs are matching these expected outputs or no. And these bits are the mask bits. Mask bit is, it tells the test bench whether it has to check that condition or not. Let's say, suppose you don't want to check some condition or some input output pair, you can set these bits to 0, 0, and your input, those particular input outputs won't be checked.
Hello.
Hello, yeah.
So why 1 1 or 0 0? Why not only 0 or only 1? Like 1 0 or 0 1 would play a difference.
No, no. About what you are asking, about outputs or about this mask bits?
Yeah, these mask bits only. Why 2 bits? 1 bit would do the
Yeah.
work. No?
No, for each output. For each output bit, I have to check, right? So for each output, I have to have each. So each mask bit covers only single bit of the output bit. So I need 2 mask bits for 2 output bits. Similarly,
Cool.
if you have more number of output bits, you need more number of mask bits as well. Okay. Okay. Now we will see how to generate this trace file, because now I just have 3 inputs and just two outputs. So it was quite simple for me to write it down directly. But it may not be always. Let's say if you have 8-bit inputs, in that case it will be very long and you will have to keep on writing each of them, and there itself there is a chance of making some error in it. So you will have to automate this process. For this you can use a C code. I think most of you might be familiar with C. So you will have to write a proper file handling kind of C code in which you will have to consider each case, I mean each input, and then calculate the expected output, convert all of them into a binary format, and then store in this trace file.txt. So I won't go into details of this C code. I will just explain the Python code. So this Python is also another way of doing that. I will open this Python file. Yeah, so most of you might be familiar with Python as well. So I am basically opening this file in a write mode, trace file.txt in the write mode. Then just to specify that there are 3 inputs and 2 outputs. And this is a for loop. So for every iteration, it will consider each input and then calculate the expected output and then just write it into that file. So for that, I have made this loop. And this range basically tells for how many times it has to iterate. So this test length, whatever 2 raised to, this is raised to, so 2 raised to whatever input length, for that much times I have to run this loop. Then this input string, this tells me that I want to format my string or format the input. Let's say my input is some number, some integer. Let's say it starts from 00 and goes up to 111. So this integer, it will format into a binary format with 3-bit values, and it will store it as a string. So this statement says that it will convert it to a string in this format. Here, if you have different number of inputs, this 3 may vary. It may become 4 or 8, whatever you require. Then here I am calculating the output. So this is sum and carry. But since we have inverted, we have put some LSB as carry and MSB as sum, I am having to invert my expected output as well. So I have inverted them over here. These are simple expressions. I mean, even if you Google out what are the Python operators, these are similar to C, these operators work. So this is the OR operator, this is the right shift and left shift operators. So I have arranged my output accordingly. And then again, I convert this expected output into a string format. And then I write it into a file where first I should specify this input string, then I should put a space in between, and then I should put a output string, and then these 1 are the mask bits. Now this should be, let's say if you have 3-bit output, then this should be 111 in similar manner. And then once the loop completes, this is F close. So this will close the file. So if you run this code, you can generate that trace file that I have just showed you. Now how to check the output file, because I have shown the output file previously. If you go to your main project folder, if you can see, there is a simulation folder in this. So go into simulation folder. There you will see model sim. So go into that folder. So here you can see this trace file and outputs. So this is the output that is actually obtained from our design for each applied input. So this is the applied input and this is the actual output that we obtained. Okay, so do you have any doubts over here up till now? You may speak out if you have any doubts. Okay, fine. So I will go ahead. we saw the simulation for simple RTL, and now we basically want to put it in our FPGA, and we want to see after actually fitting the design, that is called fitting, or we can call it as place and route. So it will apply each resources available in the FPGA. It will allocate each CLBs to it, and then after that we can again simulate our design. So I will first compile our design. So it will take some time to compile. Here I can see that there are no errors, and in the left side in tasks you can see various different kind of options. I will go into the fitter or place and route. I will see the technology map viewer post fitting. Let's say suppose I have done this fitting and I want to see in which exactly logic block or which logic element is my design sitting over there in the FPGA. I want to actually see it physically, that where exactly is my design located, and if I later on find that there is some delay in it, then maybe I can debug my problem. So for that I will open this technology map viewer. I will just show one block. I will show this full adder instance. You don't need to do this again and again. This is just to see for the first time that how exactly it looks when it goes to the chip. So I will click the locate node option, and in that I will locate in the chip planner. It will take some time. Yeah. So this is our complete CPLD chip. These are these logic elements, and these are the IO blocks on the border, and these are different smaller components in our chip, and our design is exactly sitting over here, these red ones. So this is our full adder, and if I double click that full adder design, I can see that what is inside my logic element and how it has been allocated. So since you can see over here, my full adder doesn't have any storage, or it doesn't have any register. So you can see that this is a register block which is not used at all. It is not connected to any output. You don't need to see this always. This is just to show you that this is what it happens inside the FPGA or a CPLD. Yeah, this is Max Pi chip. We have seen where it is located. This is not useful for small designs such as our full adder. This is actually useful to debug very complex design where it might be possible that the tool is not optimizing our design, and we want to check what the problem is there. So this feature is useful for that. I'm closing this chip planner. Now since I have fitted my design in my device, I want to check how is the timing. I mean, does my design get delayed? Does my output get delayed? Or is there any glitches in my output because it has been fitted in my device? So for that, I will go to Tools, then Run Simulation Tools. And in that drop down, you can see a gate level simulation option over here. So you can click on gate level simulation.
Gaurav, again there is delay.
What?
There is lag.
Oh, okay. I'm sorry. I will just repeat it again. Hello.
Yes.
Yeah. So I will repeat it again. So in tools, go to run simulation tool and click on gate level simulation. Is it visible?
Yes.
Okay, so now I will click on this option. Now it will ask me EDA gate level simulation. It will show a dialog box, and in that dialog box, it will ask me timing model. So there is just one option, slow model, but maybe in other devices we get different kinds of models, the fast model or all different combinations. So we just have one possibility. So we'll select that and click on run in the dialog box. Yeah, so if your model sim is already open, as in my case, it will show an error. Your Quartus will show an error. So first you should close your model sim and then run the gate level simulation. So I'm closing my model sim. Then I go to tools, run simulation tool and gate level simulation. And in the dialog box of the EDA gate level simulation, I click on run. It will take some time to launch model sim. Yeah, so here you can see that model sim has been launched. I will just zoom out this web window. Yeah, so here you can see that this was not appearing earlier, this red line that you can see over here. Can anybody tell me what is the meaning of this UU? I mean, what is this U? What does this U mean? Can anybody write in the chat box? Yeah, correct. So correct. And then after this UU, I can see some XX. And what does this X mean? Yeah, it's correctly written that because the circuits have delay, we have to wait for some time after applying the input to observe the output. But what does this XX mean? I can see this X in my output. So what does this mean? What should I interpret from this? Yeah, correct. It's an unknown value. I mean, either my circuit is in transition or there is some 1 and 0 that is conflicting in between, and I'm getting an unknown value. So I will continue from here. Now let's take, so here, yeah, again in this transcript you can see success, all test cases have passed. Now let's consider some test cases where we can see failure. So where can be the failure when we actually do the gate level is when, if you say you don't wait for long enough. Let's say you, instead of waiting for 10 nanoseconds, I will wait just for 5 nanoseconds. So for doing this, I will go to my test bench and I will reduce that waiting time to 5 nanoseconds and check what happens. So I have gone to test bench and then here you will find one comment, wait for the circuit to settle. So below that comment is actually this time that I have to wait for. I will wait for just 5 nanoseconds. I will save this test bench. Yeah, Here, whenever we make any change in the test bench, we actually don't have to recompile the whole design, because model sim takes care of this test bench. So in the Quartus, we don't have to actually recompile the whole design again. So I have made this change in my test bench. I will close my model sim and relaunch my simulation. So in Quartus, I again launch my simulation. Yeah, so in this transcript window, if everybody can see this, we can see an error, a failure, some test case have failed. So this is how the failure may be caused in actual implementation. In the RTL, it might work, the same thing might work in RTL simulation, but when I go to gate level simulation, it will give such kind of error. Now I want to find where the error is actually. Let's say I want to debug my design. I have made some design and I see this error. So how do I find out where that error is, or for which test case such a error appears? So for that, as we discussed earlier, that we can see the output file of this test bench. So I'm going to the outputs file. Again, the output file is located in the simulation directory, and inside that in the model sim directory. Here you can see output. Now we can see it says error line 1, error line 2, error line 4, because all these test cases are getting violated because there is a slight delay in the output. So this is how the actual implementation might affect your design, and you may not get the expected results from your design. So it's very important to perform a gate level simulation before actually implementing in an FPGA. Similarly, now let us consider one case where the input is wrong. I mean the output, let's change the expected output for some time in the trace file. I'm changing this 110 case to the output to 11, and let's check for that what happens. Now I am in model sim. To relaunch my simulation, I will just click the in the transcript window, I will place my cursor and I will just click the up arrow so that my previous command will get repeated. Now this command was put by Quartus, so it will relaunch the whole process again. So I will just enter. Yeah, one thing I forgot here is I did not change the delay in the test bench. I will just correct that delay to 10 nanoseconds again. And again, I will relaunch my simulation. Yeah. So now here you can see in the waveform window that I am getting my output in time, but the issue is that still I can see the failure over here because I have made changes in my expected output. So it is correctly identifying my test bench is actually working. It is identifying a error case. This is what I can conclude from this. And the last case that is remaining, that is, let's say I want my test bench to ignore this error. For some reason, I don't want my test bench to look at this particular input and output pair. I want it to ignore this particular case. So for that, as we know, we can put these mask bits to 0, 0 so that it will completely ignore this case. I have put it to 0, and now let us simulate again. So now you can see in the transcript window that we can see success, all test cases passed. Because I put 0 in that mask bit, you can see here that this particular bit that I put was wrong, and this bit is correct, but the MSB of the expected output was wrong, and I just masked it by putting a 0 in this, and my test bench actually ignored that bit, and now it is showing success. So my mask bits are working. So anybody has any doubts up till here? You may raise your hand or you may speak out. Hello. Will anybody tell, like, if you don't have doubts, you can say no or something like that in the chat window. Okay, fine. Okay then, so up till now what we saw is how we simulate the whole thing, how we simulate our complete design. But after, from the next session, we will see how to actually implement, how to do this pin planning, how to actually program our device. And then there is a testing and automatic testing that you will see in the next sessions. For now, the demo is over. So now we have to go into your respective channels, and there you just take care that while logging in, you have to log in to the general channel and not the evaluation channel. There are two channels, two meetings open in your channel. One meeting will be for general meeting where all of you, all the students in that channel will have to join, and your TAs will announce whenever they have to ask you questions or whenever you want to ask them some personal doubts. You can go to a different meeting and there you can connect to them. So just take care you join the proper meeting.
I have a small announcement to make. Hello? Gaurav, are you done?
Yes, ma'am, I am done.
So actually I have posted a message on Moodle about the boards that we have sent. So about 50% boards have been sent and we will start receiving them. And you are supposed to send us the acknowledgement. I will create a submission link and please post, and I have given the instructions there, and please do that. You will receive both digital, that is Krypton and PT51 boards together, but then send the acknowledgements in two different model groups. Okay? Now you can, I think, go to your respective channels and start the experiment.
And I think
Ma'am,
recording can stop now.
Yeah, we will
Please
stop recording of this
recording.
meeting. Yeah.